Okay, so today we are going to talk about number 13, and it is called the Rayleigh quotient. So this Rayleigh quotient has a lot to do with the symmetric matrices. So let's recall some basic property. So first of all, every symmetric matrix has its eigenvalues all real. And this is not always true. If you just put some matrix and then calculate its eigenvalue, then you will notice that some of the eigenvalue has some complex number. And for this class, we focus on symmetric matrices, and so most of the time, the things are nice. One of the nice things about the real numbers is they can be ordered from small to large. So we can say a symmetric matrix has eigenvalues from lambda 0 up to lambda n minus 1, and they are ordered by its quantity from small to large. So an immediate question is, suppose we are going to use these eigenvalues for the application in the future, how do we going to find that? How are we going to find that, right? How to find it? So if you took any linear algebra course before, then there is an algebraic way. But somehow if you did not take any course like that, then that's fine, because I'm going to tell you this is not a good idea in this class, at least. So maybe you heard of the characteristic polynomial. So traditionally, most of the students doing linear algebra will try to learn this polynomial. It's just a polynomial of degree n, and all you need to do is try to calculate this one and try to solve the root. Solve px is equal to 0. And you will get some numbers, and they are the eigenvalues. But the drawback is you basically don't want to do this by hand. Calculating the characteristic polynomial, it takes a while, and also solving the polynomial, it is not a trivial work. And in particular, many cases, humans just don't know how to solve a polynomial. So this part is more like a theoretical way, and like what I say, if you haven't heard of this before, then that's totally fine, because I'm going to tell you a different way that can help you to find the eigenvalue. So the other way is the numerical way. It will give you an approximation of the eigenvalues, although it is not precise, but it is more straightforward. So that's why we are going to talk about the Rayleigh quotient. And later on in the next lecture, we are going to talk about the power method. And so Rayleigh quotient is more like a theoretical background, and the power method, by its name, it is a method. It is an algorithm to find the eigenvalue. So Rayleigh quotient ensures the algorithm in the next step is going to be true. All right, so the main topic for today, or at least in this hour, is two parts. The first part is, what is the definition of a Rayleigh quotient? Okay, So Rayleigh is a name of a mathematician, and quotient just of means something of this form, a over b, right? More like a not it just like a fraction, and in Chinese we call the 分数. Okay, and once we will formally define that. I'm just saying that this term in Chinese means a division, or the result of the division. And for the second part is why, and why we care about that, and what's the application. Okay, so basically what and why. So let's start with the definition. Part A. Let's say we have a matrix which is n by n and the symmetric matrix. And we have a vector, and it is in n-dimensional. So the definition is the following. The Rayleigh quotient of x with respect to A is this form. Okay, it looks like x transpose ax divided by x transpose x. And on the left-hand side, this is just a notation. Okay, you need a and x in order to obtain this formula. It will be easier to just look at one example because it takes a while to digest that. So let's see if we can set A as a 2x2 symmetric matrix, and we can set arbitrary x, and let's say x is equal to 1, 1. Okay, so you see now n is equal to 2, and we're going to calculate the Rayleigh quotient of this guy. Let's do it one by one. First is the numerator, and in the numerator you will make the x horizontal on the left and make the x vertical on the right, and put the a in the between. So in this case, we are treating x as a kind of column vector, and or it is a 2x1 matrix. So through some calculation, you will realize that it is equal to 8. But this 8 is actually a 1 by 1 matrix. On the other hand, we got x transpose x, and this is going to be a horizontal x and a vertical x. So their product is equal to 2, and again, it is a 2 by 2. It is a 1 by 1 matrix. So I want to point out that this is like a convention that there are actually matrices, right? So these two, there are matrices, but they are treated as numbers because they are just 1 by 1. So when you do the Rayleigh quotient, you simply take 8 and then divide it by 2. And moreover, now you know how to calculate what is the meaning of the Rayleigh quotient. It's just a formula, right? And I want to tell you that, emphasize that this is actually just the inner product of x and x. And it is equal to the length square of x. And if you wish, this part can also be written as the inner product of AX and the X. Okay, but sometimes it is important, sometimes this is just redundant. They are equivalent. This is the same way to write that, and this is the same way to write that. So some people will write it as AX inner product with X divided by X inner product with X. So naively or intuitively, this quantity is saying when you have X and then you plug that in and try to see how much you will get bigger. Say if X after AX it becomes 3X, and then U becomes 3XX and divided by XX, so the ratio is 3. And that's roughly the idea. How much the matrix A can enlarge this vector. But anyway, I will just let you know the theorem, and let's look at the fact. So far so good? 有问题吗? Or okay, again, you can ask me some questions later. Okay, if you don't want to do that publicly. Okay, so anyway, this formula is just it is just a formula, right? You have X, you have A, then you should be able to calculate what are these. Okay, it is a function of A and X. Okay, now this is part B. I better to be a bit faster. So why? So the reason of the Rayleigh quotient is it can help us to understand the behavior of the eigenvalue. So recall that A has is an n by n and symmetric matrix, and such a matrix can have the eigenvalue all real, and we call that as lambda 0 up to lambda n minus 1, and they are all real, so we can order that from small to large. And not really necessary, but we can say the corresponding eigenvectors are v0 up to vn minus 1. So the theorem is the following. Some people just call that the Rayleigh quotient theory. Or some people call that as the min-max theorem. But anyway, just suggested by its name, if we look at the Rayleigh quotient, then we know when we do the Rayleigh quotient, x cannot be 0. Otherwise, the denominator is going to be 0, which is not good. And if we consider all the possible x, which is not 0, and we take the maxima over all the possible x, then Rayleigh quotient theorem tells us it is going to be the largest eigenvalue. And that's the power of Rayleigh quotient. Similarly, you look at all the possible Rayleigh quotient and take the minimum over all the possible x. And then it is going to be the smallest eigenvalue. So by using this, you are able to get an idea about lambda 0 and lambda n minus 1. This is a bit different from what we learned before, because previously, if you solve the solution, if you solve the characteristic polynomial, like here, then you will get all the solution at the same time. You don't prefer a particular one. But in this case, we prefer the largest one and the smallest one, and it can help us to understand the matrix a bit better. And there is a note or a remark. the note is saying, if you look at the Rayleigh quotient and plug in kx instead of x itself, then according to the formula, it will become k squared x transpose ax, because the kx will appears 2 times, and you can pull the k outside. So there is a k squared on the left. And there is also another k squared at the bottom, because x transpose x has 2k insides, and so there is a k squared on the left. So if you replace x by kx, they are going to be the same. So if you have a vector x and you have a longer vector kx, and they have the same Rayleigh quotient. So this means if we want to take care of this maxima, we don't need to look at all the possible x. We just need to pick one x on every straight line. For one straight line, we just pick one and with the unit length. So all we need to care about is the maxima over all the x with length equal to 1. And this time, because the length is equal to 1, so we can ignore the denominator. All we need is the top. Similarly for the minimum one. Okay, I don't have time to talk about the reasoning, because if I have time, maybe I will do it later. But let's do one more things. So you notice that this help you to know what is lambda 0 and lambda n minus 1. And what if your algorithm want to find out what is lambda 1, 2, 3, 4, something like that. So in fact, this is quite a comprehensive theorem. It has a lot of way to deal with this. So for example, moreover, if you already know this part, but anyway, if you solve the first optimization problem and find out what is the x, and that x is going to be v0, and if v0 is known, okay, under this circumstance, you are able to calculate what is lambda 1. And it is taking the minimum of all the Rayleigh quotient. And again, we look at all the non-zero vectors, but this time, we focus on those vectors that is perpendicular to v1. And the reason, sorry, it is v0. The reason about this is when A is an n by n symmetric matrix, all these vectors are going to be orthogonal. So once you already know one of them, the remaining part are going to be orthogonal to that. So this idea, the intuition of this formula is saying, I only focus on those parts that is perpendicular to v0, and then I'm going to take the minimum, which is this one. So it is going to be lambda 1. Okay, so that's the idea of getting lambda 1. And if you want to do lambda 2, you have to have v0 and v1, and you look at all the vectors that is perpendicular to v0 and also perpendicular to v1, and then you are able to find out what is lambda 2. So I will stop here, but meanwhile later on I will write some kind of the idea behind the scene. It is not too bad. It is don't treat that as a proof. When you say a proof, it sounds scary, but I just want to give you some reasoning. But I will write it on the next slide, and you can feel free to do some discussion or work on the exercise. So I'll stop here.